I mean, honestly, if this doesn't blow your mind, do you even have a soul? The Towers of Hanoi problem is a classic recursive problem that can cause endless amounts of frustration. When I first encountered this problem, it took me several days to come up with the solution, and quite honestly, I didn't feel like I understood the solution until after teaching it to many of my former students years later. The setup of the problem is as follows. You have 3 rods. One of the rods has some number of discs of varying sizes placed on it, with the largest disc at the bottom and the smallest disc at the top. Your goal is to move these discs one at a time to a particular destination rod in the same configuration as the start. Before you get ahead of yourself and declare this problem trivial, there is one important catch. At any point in the process of moving discs, you are not allowed to move a larger disc on top of a smaller disc. This rule is what makes this problem significantly more challenging to solve. In this video, we will dive into the Towers of Hanoi problem in 3 distinct phases. First, we'll approach it from the perspective of a puzzle, where we'll try to come up with a strategy for various configurations. Then we'll transfer the strategy into a recursive program to solve this problem for any number of disks. In this section, I'll also show you some helpful tricks to solve challenging recursive problems like this one. And lastly, we'll deconstruct the recursion to understand what's really going on underneath the hood with some nifty animations that I'm pretty sure you won't want to miss. So make sure you stick to the end of the video. Alright, let's get started. Let's focus first on 3 disks, since the solutions to the 1 disk and 2 disk setups aren't too interesting for analysis purposes. I highly recommend pausing the video and taking a second on your own to see if you can find the set of moves to get these 3 disks to the rightmost rod. Our goal is to come up with a general strategy for solving this problem. If you're like me, your first go-to strategy in any type of puzzle is random guessing. And honestly, there's no shame in that. Random guessing is the oldest strategy in the books. So if I'm looking at this problem, the first thing I might try is to move the smallest disk to the middle rod. And then the next move is basically forced from there. I would move the green disk to the rightmost rod, since I can't move it to the second rod because that would violate the rules. After that, the next move that makes the most sense is to try and move the smallest disk to the rightmost rod. And at this point, after I've finished completely destroying the order of this problem with 3 random moves, I think it might be a good idea to evaluate what I've done so far. Well, unfortunately, it's not looking too good. It looks like we are a little bit stuck because what we really want is the bottom disk below the disks that we currently have on the 3rd rod. What we just did by random guessing seems to be pretty counterproductive to that point, so at this point in the problem, I might decide, okay, I might just want to start over and reevaluate. But from this random guessing experience, we've learned one important fact. We need to first think about moving the largest disk from the first rod to the destination rod. And if we take this idea one step further, before we can even think about doing that, we're going to have to deal with the top 2 disks. And we have to deal with them in a careful manner so we can eventually move the largest disk to the destination rod. This means our only option is that we have to find some way to move the top 2 disks to the second rod. Okay, so now that we split our problem into more reasonable subtasks, let's solve them one by one. To move the top 2 disks to rod 2, we first move the smallest disk to rod 3, after which we move the middle disk to rod 2 and finish up the subtask by moving the smallest disk to rod 2. And now we are free to move the largest disk to rod 3. Alright, so what's next? Well, from here the solution is actually pretty clear. We need to move the top 2 disks from the second rod to the 3rd rod now, and to achieve this, we move the smallest disk from the second rod to the first rod to get it out of the way. We then move the middle disk from the second rod to the 3rd rod, followed by the final step of moving the smallest disk to the destination rod. And there you go, we've just solved Towers of Hanoi for 3 disks. Here's a quick recap of what we did. We first found a way to move the top 2 disks to the second rod, allowing us to then move this largest disk to the destination rod, and after this, we finished off by moving the top 2 disks from the middle rod to the destination rod. Okay, so now let's go one step further and see if we can solve this for the n=4 case by utilizing a similar strategy to what we've just developed. Before I go through the steps to solve this, take a second to pause the video and see if you can come up with the steps on your own. Applying the general strategy to this new problem, we want to now move the top 3 disks from rod 1 to rod 2. How do we do this? Well, one interesting thing about solving this problem is that it's basically like ignoring the largest disk even exists and solving a general 3-disk Towers of Hanoi problem, where now our destination is the middle rod. Make sure you take a second to understand the mapping that we just did. And looking at this simpler problem, we know how to solve it now, right? We basically solved a version of it earlier. To solve this subproblem, we move the top 2 disks to the third rod. We achieve this by moving the top disk to the second rod, the middle disk to the third rod, and finish off by moving the top disk from the second rod to the third rod. This now makes way for the largest disk moving into the desired position. And now to finish off the subproblem, we once again move the top 2 disks, but this time from the third rod to the second rod. This subtask breaks down into moving the top disk to the first rod, followed by moving the second disk to the second rod, and ending with moving the top disk from rod 1 to rod 2. Notice the logic that we used here was essentially the same as what we did earlier, and this is something that will be immensely important going forward. In a sense, this is where the recursion of this problem really originates. Going back to the 4-disk problem, we now move the largest disk from the first rod to the destination rod. And now, following our earlier strategy, we now move the top 3 disks from the second rod to the destination rod. And the pattern once again shows up. This is essentially the same 3-disk problem we've solved many times now. We move the top 2 disks from the middle rod to the first rod, and to do this, we move the top disk from the second rod to the third rod. We then move the second disk from rod number 2 to rod number 1. And we finish the subtask by moving the top disk to the first rod. We then move the third disk from the second rod to the destination rod, and our final subtask is to move the top 2 disks from rod 1 to rod 3. Once again, we know how to do this. We move the first disk from rod 1 to rod 2, move the second disk to the destination rod, and finish off the whole problem by moving our top disk to the destination rod. And that's the sequence of steps for Towers of Hanoi with 4 disks. I know that was a lot, so let's do a quick overview of what we just did. We first moved the top 3 disks from rod 1 to rod 2. This required a couple of intermediate steps where we first moved the top 2 disks from rod 1 to rod 3. Next, we moved the third disk to the middle rod, and then finished the subtask by moving the top 2 disks from the last rod to the middle rod. We then moved the largest disk to the destination rod. And lastly, we finished by moving the top 3 disks from the middle rod to the destination rod, which had the same set of subtasks we've encountered several times. So now that we have a fairly good understanding of a strategy for this problem, let's now dive into a formal problem statement. We want to write a function Hanoi that takes 3 inputs, n, start, and end, and outputs a sequence of steps to move n disks from the start rod to the end rod. Here's a quick example of an input and output so that we understand how this problem statement works. If we pass in n equals 3, start is equal to 1 and end is equal to 3, what that means is our start rod is in rod number 1 and we have 3 disks on that start rod. Our end rod is rod number 3 and that's where our disks need to reach. For simplicity, let's assume that the start and end will always be between 1 and 3 and that they will never be equal to each other. Let's also assume that n will always be a positive integer, so we won't have to handle any weird edge cases. For this particular input, the sequence of steps that this function will output will look like the following. We've already gone over how these steps are generated from our strategy, but here's a quick overview of how the steps correspond to actual movements of disks. The basic interpretation is that A pointing to B means that we're going to move the top disk from rod A to rod B. Okay, so how do we get started on solving this problem? When I'm looking at any sort of challenging problem, I try to find the easiest thing I can do to help me solve the problem. Personally, I've noticed that there's definitely an intimidation factor in tough problems like this, and knocking out something easy can help you get over that initial intimidation. One of the easiest things we can do here is define a helper function that simply prints a move in the appropriate format. Defining this function is fairly straightforward to do and looks like the following. So now that we got that out of the way, let's shift our focus over to the main task. We need to find a way to programmatically generate a sequence of steps for n disks. We've already seen many clues in our investigation that point to the fact that we'll have to solve this problem recursively. But how in the world can we come up with something that works? This is by no means an easy problem, and before we get into that solution, I want to take a quick aside to go over an incredibly important concept when solving recursive problems. Whenever you are faced with a challenging recursive problem, there are 3 key steps that you should follow to make your life exponentially easier. These 3 tips have helped me throughout my years of learning computer science and saved me a lot of pain. The first step when solving a general recursive function f of n is to design a solution that works for f called on the input 1. This is often referred to as your base case. The second step is the one that's the hardest to accept, but what we are going to do is we're going to just go out on a limb and assume that f called on the input n-1 will work. The second step is often referred to as the recursive leap of faith. Once we've made this assumption, we will then show how we can define f called on n in a working manner using the function calls to f on n-1. Here's some intuition for why these 3 steps work. Think about solving this recursive problem f of n as trying to knock down n dominoes, where you only get to knock down the first domino. You want to show that the nth domino will eventually be knocked down. How do you do this? Well, you know that if you just have one domino, it's obviously going to work out because you can just knock it down. This is an analogy to step 1. From here, what you can do is just assume at some point the n-1th domino will eventually fall. This is the analogy to step 2. And now, to guarantee the nth domino will fall, we have to put this domino just close enough to the n-1 domino so that when that domino falls, the nth domino will respectively fall. This is the analogy to step 3. And once we do that, all the dominoes fall. I want to emphasize here that all 3 steps are equally necessary for this to work out. If we don't get the base case right, that means the first domino never falls. If we don't make the assumption that f called on n-1 works, that's similar to the situation where the n-1 domino never actually falls, in which case there's no way that the nth domino is going to fall. And lastly, if we don't properly define the relationship between f of n and f of n-1, that's basically like putting the nth domino too far away from the n-1 domino, so in that case the nth domino also never falls. It's by moving the domino close enough to the n-1 domino that the nth domino falls. So let's now apply these 3 steps to solving towers of Hanoi. Starting with step 1, we want to show how we appropriately handle the base case for this problem when n is equal to 1. That's easy enough, since if we only have one disk, all we have to do is move that one disk from the start to the end. In our problem statement, this is equivalent to calling print move with the arguments start and end. That takes care of step 1. Now let's move to step 2. In the process of solving towers of Hanoi for any n, what it means to assume that f of n-1 works is that we can just accept that any version of towers of Hanoi called on n-1 will work. It's important to remember that this includes a variety of starting and ending positions, and we're just going to assume that all of these subproblems work. Now, with that assumption that any call to towers of Hanoi on n-1 works, let's move to the third step where we need to show how we can solve n-disk towers of Hanoi problems using the solutions to towers of Hanoi called on n-1. There's one minor issue though. The first thing we need to take care of is we currently have a reference to the start and end rod, but we somehow need to have a reference to the other rod in the process. One quick and easy way to do this is by utilizing the rod numbers. Since the first, second, and third rods are labeled 1, 2, and 3 respectively, the other rod will always be 6 minus the sum of the start and end rods. And now that we have the other rod, we can now execute the first step of the strategy that we developed earlier. We want to first move the top n-1 disks from the start to the other. The neat thing about the framework that we have defined for solving this problem is that the first step is exactly equivalent to solving the following towers of Hanoi problem on n-1 disks. By the second step of recursive problem solving, we can assume this call works, so we can use it as part of our solution. This corresponds to the recursive call to Hanoi called on n-1 start and other. Once we've completed this step, we can then proceed to moving the last disk from the start to the end. This corresponds to a call to print move with the arguments start and end. And now the final step is to move the top n-1 disks from the middle rod to the destination rod. This subproblem is essentially the same as solving Hanoi for n-1 disk, where the start disk is the middle and the end disk is the last disk. This means we can assume that the subproblem works as per our framework, and the corresponding recursive call is Hanoi with the arguments n-1, other, and end. And following these steps successfully solves Towers of Hanoi for n disks, and this does indeed end up being a valid recursive solution. Now, before we move on, I want you to take a second and look at the final logic, and really take a moment to appreciate it. I mean, how crazy is it that such a seemingly tricky problem ends up having such a simple solution? I remember when I first solved this problem, my mind was absolutely blown away. I mean, honestly, if this doesn't blow your mind, do you even have a soul? This is really an amazing example of the power and beauty of recursive problem solving. And for completeness, here's a fully developed solution to this problem in Python. The nice thing about going through all this work is that the code basically writes itself. Now, at this point, some of you might be looking at the solution and think, okay, I understand how it works within the recursive leap of faith framework, but how does the actual recursion work? Fear not, let's answer that question. I think the best example to take a deep dive into is the one we started off with, Hanoi with 3 disks, where we want to move the 3 disks from the first rod to the third rod. The first recursive call will call Hanoi on 2 disks with the start rod as rod 1 and the end rod as rod 2. Here's what that represents. This recursive call forces us to go back into the function where we now get another recursive call to Hanoi, this time on 1 disk, where we want the single disk to move from 1 to 3. Here's a visual example of what this call is trying to achieve. And this recursive call will go back into the function where we actually hit our base case, which then prints the move from rod 1 to rod 3. And this is our very first move in the Towers of Hanoi problem. Visually, what this represents is that all our recursive calls before have changed state because we now have officially made our first move. After making our first move, we have officially completed the recursive call to Hanoi on 1 disk, which now means we have to complete the recursive call to Hanoi on 2 disks. This means we now have to call print move on rods 1 to 2, which has the following effect. This is the second move in this particular Towers of Hanoi problem. After completing the second move, we still have to finish computing the recursive call to Hanoi on 2 disks, which now makes its final recursive call on a single disk from rod 3 to rod 2, which has the following visual representation. This hits the base case once again, where we now make the third move, which is to move the disk from rod 3 to rod 2. Here's the effect of that on the overall problem. And this now completes our first original recursive call, which was step 1 in our earlier strategy of moving the top 2 disks from the first rod to the second rod. What's next is step 2 of that strategy, where we move the last rod from rod 1 to the destination rod. That's a simple print call, which has the following effect. That actually ends up being the 4th move in this sequence. This now leads us to the final step, which involves moving the top 2 disks from the second rod to the destination rod. That kicks off the following recursive call. This kicks off a similar sequence of events. The second recursive call goes back into the function, where we now make a recursive call with 1 disk moving from the second rod to the first rod. This hits the base case, where we now print this move, which is where the 5th move in the sequence comes from. Here's the effect of that on the overall problem. The 6th move then follows by now moving the disk from the middle rod to the destination rod. Here's the effect of that on the overall problem. And finally, the 7th and final step involves the final recursive call on 1 disk moving from the first rod to the third rod, which once again hits the base case that actually prints out the last move. And there you have it. That's how the Towers of Hanoi recursion unravels. It's really quite amazing how it all works out, especially if it's your first time seeing it, so I highly encourage working through some examples on your own to convince yourself that things do indeed work out as they are supposed to. Before I conclude this video, here's a big picture recap of how we went about solving Towers of Hanoi. We first took a step back, didn't even think about the code, recursion, algorithms, or anything, and just tried to understand how we as someone trying to solve a puzzle might go about solving this problem. This is something I really encourage doing when you encounter a tough problem. Don't be afraid to take a step back and take a look at things from a different perspective. Following this, we developed a strategy and used that strategy to implement a recursive solution. On the way here, we learned about the recursive leap of faith and how it can help us simplify particularly challenging problems. And lastly, we took a step deeper into the problem to understand how this recursion works out. Thanks for watching me, and as always, I'd appreciate it if you hit the like button if you enjoyed it. If you want to see more content like this, be sure to hit the subscribe button, and if you want to more directly support this channel, be sure to check out the Patreon page linked in the description below. See you in the next video.